This is part two of our review of the power, momentum, and impulse summative. Number 7, I'm going to go over this second page of multiple choice questions here. So it says, what is the average power supplied by a 60 kilogram person running up a flight of stairs a vertical distance of 4 meters in 4.2 seconds? And this is a power problem, and power equals work over time. The work that this person has to do is really the work of overcoming the force of gravity, which ultimately kind of makes sense from an energy conservation standpoint, that the work that this person puts in has got to equal the amount of gravitational potential energy that they have at the end of the climbing the stairs. So that's where this mgh ultimately comes from. And we're dividing it by time to get the average power. So if you take 60, I just kind of work it out in my head. If g is equal to 10, then this is just 60 times 10, which is 600. We know it's a little bit less than that. And I'm just going to multiply by h and then divide by t. But notice, like, h and t are almost the same. Because t is a little bit bigger, this is like just multiplying by something that's a little bit less than 1. So if this is like 600 times something that's a little bit less than 1, it's going to be something a little bit less than 600. I get to 560. Of course, you can plug in m, g, h, and t from your calculator, and you should get something around 560. Number 8 is just a momentum question. A bullet is shot vertically into the air and it reaches a certain height, and then it falls to earth. The momentum of the bullet is really related to this very simple equation, P equals mv. Surely it's not zero throughout the trip, because when it leaves the gun, it has a mass and a velocity, so it has a non-zero momentum. It's greater when it leaves the gun than when it reaches its maximum height, because the velocity when it reaches its maximum height is zero. So the momentum when it leaves the gun is greater than when it reaches its maximum height. So we'll just move on here. Number 9. Task B requires half the power output of task A and is completed in half the time. And the work required for task A is, and we have to compare that with the work required for task B. So I'm going to take my power equation and solve it for work right here. And then I'm just going to guess or just pick some numbers. I'm going to say that, let me just say that the work for task B is going to be a power of 100 watts times 4 seconds, and that's 400 joules. Well, now let me figure out for A, right? It says task B requires half the power of task A. So that means task A must require 200 watts if task B requires 100. And it's completed in half the time. So task B is completed in half the time that task A it takes. And so I had 4 seconds here. Task A takes twice as long, and so that's 8 seconds. And when I multiply that out, I get 1600. Well, that's 4 times as much as 400. So my choice is D for that problem. And again, it just comes back to using the formula. And in this case, I just picked some numbers that met the requirements of the problem in order to have sort of a specific set of numbers to compare at the end. Number 10 I threw out largely because for C and D I should have put 15,000 instead of 1,500, because that's what a kilo means. And so that was a typo on my part. There is no correct answer. Really, the correct answer would be 15,000 joules of electric energy, that is, every second. That's what 15 kilowatts is. So if the time it takes to bring a moving object to rest is tripled, then the force required to stop the object is divided by 3. And this is a impulse momentum problem, impulse momentum theorem problem. Notice that the time it takes to bring a moving object to rest is this time. And we're bringing it to rest. We're basically changing the momentum of the object by the same amount. So if this thing is decreased by a factor of 3, then this thing has to increase by a factor of 3. So or I have it backwards here, if we triple the time that it takes, then we divide the force required by 3. And that makes sense. If you give yourself more time to stop an object, then you don't have to apply as big of a force. When comparing the momentum of two objects, which of the following is always true? Again, this is just a P equals mv problem. The more massive object will have more momentum if the velocities are the same, A. And then all of these things are true about 1 watt except for C. This is actually an attempt to describe what a newton is, not what a watt is. A newton is the force that's required to accelerate a 1 kilogram mass by 1 meter per second in 1 second. But that is not the definition of power. And if you consider the power equation, this equation right here, then you see that you can also take this form of this equation, and that's what B and D are getting at. A watt is doing 1 joule of work in 1 second, which is the same as applying a 1 Newton force over 1 meter in 1 second. So the answer is C. That's the oddball in this problem.